All right, guys, 11.8 is what we're looking at here. This is the last section of the book. We made it. Well, almost. We got to finish this section first. This one's talking about spheres. So three-dimensional circles, talking about spheres, all about it. We got some vocab going on. And then we get into surface area and volume of the spheres. So that is what 11.8 is on. If we look at a chord of a sphere, it's exactly like the chord of a circle, only it can go in any direction, right? Because it's three-dimensional. It doesn't just have to go along one specific circle. It's the same thing as the radius of this circle, right? A chord of a sphere would be to any point in the sphere, and it's hard to imagine that three-dimensional from my drawing, but it could be out to this point on the sphere as well, right? So that's a chord of it. A great circle, I guess that's the next big thing here. The great circle is going to be sort of like the equator would be if the Earth was truly a sphere, which it's not, by the way. I know maybe you've learned that it is, but it's not exactly a sphere. The poles are squished down. Google it sometime. You'll learn something. So a great circle would be like the equator or the prime meridian, and then the other side. It's just a circle that goes all the way around the Earth. If you were to slice it along it, or the sphere, I guess, if you were to slice it along it, it would go exactly to the center of that sphere. Okay. So when I mentioned chord of a sphere, I was thinking radius, and radius is what we were talking about before. Chord are endpoints. Any segment that has endpoints on the sphere. So you see it here, and sorry for the confusion, but you see it there, that chord, that's a chord. If it's got two endpoints on the circle anywhere, that's going to be a chord. Over here, these were radii that I was drawing in from the center to the outside, whereas the chord could go from any point to any point and be a chord. Okay, there you go. Hopefully you caught that. If we look at surface area, and they're going to try to show why this formula is the way it is by using a baseball or a softball. It sort of makes sense, sure. It's not exact though, so we gotta go with the formula. 4 pi r squared is the area of the surface. So just your radius, whatever your radius is, square it and times it by 4 pi. And you look at the explanation using the baseball, right? You've got the leather covering that's there, and if you were to take 1, 2, 3, 4 circles, that pretty much encompasses the whole thing. It's not exact because they're not exactly circles, but you get the general idea at least, where that's one of the circles, and we have about 4 of them there. So a little bit of a weird thing there in terms of trying to explain what it looks like. As long as you know the formula, then you're all set. Just make sure we are using the radius, not the diameter. If you have that radius, you plug it in. We've got it. It's very easy to mess up this one and the volume one. So what I'm going to point out is that for surface area, remember, is a two-dimensional measurement. Even though we're looking at three-dimensional figures, area is a two-dimensional measurement. And the labels are always squared, right? Centimeters squared, inches squared. There is a squared in this formula for surface area. So area is always squared. Whereas you look at our volume formula, and our volume formula, they get into some weird stuff explaining it here. I don't even want to look at that. But our volume formula has r to the third power, right? So now volume has labels like inches cubed, centimeters cubed, miles cubed. So we have to cube our radius in our formula. So 4/3 pi r cubed is what we're looking at. A little weird with the 4/3. Make sure you have it as 4/3. Make sure you're typing it into the calculator correctly if you're going to do that. You could do the fraction button or in parentheses if you're concerned about it at all. But we're just going to plug that radius in, and then we're going to be good to go on the formula. Right? You plug in a 4.5, cube it, and then multiply by 4/3 pi, and we get it. Okay, so take a look at that, should be fine. So finding the volume, if they give us the surface area, then we work backwards. We use the surface area formula, we solve for the radius. The good news is if they give it to us in terms of pi, the pi's just cancel out. Divide by 4, we're left with 81 is equal to r squared. Take the square root, we get our radius. Then we can take the radius, plug it into the other formula, right? Composite figures, right? It's either going to be adding or it's going to be subtracting. It's going to be dug out. So you just need to figure out which one it is. One thing I will point out here on this example, this picture that they give you, it just so happens that the radius is the same as the height, and that's not always going to be the case. You could have a height be, an 8 here and have the radius of 2, which means if the radius is 2, that means this only would come down 2. So you might see something where it looks like this, where your radius is 2, which means it comes down 2, but the whole height may be something different. So just be aware of that. I will tell you on the test that you're about to take, there is a picture of something like this, but you got to trust the numbers. I said all year, trust the numbers, don't trust the picture. So just be very careful on that one is all I'm going to say. So composite figures, really that's what we're looking at, and that's it for 11.8. There's not a lot to it. As long as you know those two formulas, then we should be good to go.